Okay, so our next speaker is Aaron Swan with Specializing Scope Graph Resolution Queries.
Yes, thank you, and welcome to this talk about specializing scope graph resolution queries, which is about applying the optimization technique of specialization or partial evaluation to scope graph queries. But before diving into the specifics, let me motivate why that's even important. I mean, nobody wants to be involved in the effort of optimizing something that is not useful. So in general, scope graphs have everything to do with type checkers. And I think implementing type checkers is hard. You need to carefully stage passes over programs, build up symbol tables and all that sort of stuff. And all that manual messing with low-level details can be challenging. Therefore, I think instead we should generate or synthesize type checkers from high-level specifications. So as a language designer, you only need to think about, well, what is the semantics of my language? And a backend will take care of generating all low-level scheduling details. And a possible way to do that is using the Statix meta language. So how does that work? A language designer writes a specification of his language that includes name binding rules and type checking rules. This specification is then given to the backend of the Statix language, which generates a type checker for it. And this type checker can be used as executable to type check real-world programs. However, there's even more to it. The Statix backend can also be used to generate all other sorts of services, such as code completion. We have projects doing renaming and inlining, refactorings. And as a language designer, you get all those for free when you use Statix. And how is that made possible? Well, at the backbone of it are scope graphs. Scope graphs is a model for name binding that's used both at the specification level and at an implementation level to take care of all the name scheduling details. So before diving into the details of scope graph, let me list the advantages of this approach. First of all, it's very easy. You only need to think about the high-level semantics of the language, and everything else is generated for you. Second, we can be sure that all language services that we generate are consistent. So for example, it's not possible that our code completion service will give a proposal that later on the type checker will reject. All those services use the same semantics to reason about programs. And thirdly, because our specification is very high level, we could define a declarative semantics for that that's independent of any of those implemented services, which allows us to reason about our type systems, for example, proving type soundness. However, there is a problem. The type checkers that we generate are really slow. And well, we tried some profiling and we found out that the name resolution in these scope graphs has more than 50% overhead. And that's not what we would like. We want type checkers to be fast, to be well interactive in our editors. And in this talk, I will be explaining how I applied partial evaluation on these scope graph resolution queries to get rid of all this overhead. So let me start explaining what scope graphs are. I will use this example program to illustrate them. This program has a top-level definition and two modules A and B, where module B imports module A, and there's a reference X in B that eventually will resolve to the declaration in module A. In scope graphs, nodes represent scopes in a program. So in the graph that I show, there's a node S, which represents the global scope, so the scope of the whole program. In this scope, we have a declaration of A, which is modeled by another node, which is connected to the global scope using a label with a var, using an edge with a var label, which indicates that this A is actually a variable. Similarly, we have a scope for the module for the body of module A, which again has a lex edge to the parent scope to indicate that the global scope is the lexical parent of this module A. Also, there's a declaration of module A. This is modeled by giving the scope of A the name A and having a mod edge point into this A. Inside the body of A, there's a definition, which is modeled in the same way as the top-level definition. And we have a similar structure for module B, which again has a scope for its body pointing to the global scope and the mod edge pointing back to indicate it's a declaration. And we have a variable y in B. But there's also the import. How do we model imports? And this is where scope graphs really shine over the usual approach using environments. We can very simply model it by just having an edge from scope B to scope A. This ensures that everything that is in scope A can be reached from scope B, which models the usual semantics of an import. However, I haven't demonstrated name resolution yet, so that's what I'm going to do now. I marked the reference X at the bottom right corner in red, because that's a reference and we need to find a correct declaration for that using these scope graphs. So we do that using a query in the scope graph. The query starts in scope B because X is in a module B, and scope graph resolution will find a path in the scope graph that points to the correct declaration. So in this way, we bound the reference X to its corresponding declaration. However, an attentive listener might ask, why didn't it find this path? Why didn't it traverse to the global scope and then traverse the mod edge to A and find X? From a high-level perspective, this is obviously wrong. You don't want to resolve two declarations not using the import, because when this path would have been valid, it would also have resolved to X without the import statement being there, which is obviously incorrect. So what we do is we restrict the number of valid paths using regular expressions over these labels. In this case, we gave a regular expression that has a closure over lex labels, then possibly traverses an import label, and then a var label, to ensure that we can look in lexical parent scopes, possibly resolve over a single import, so we have non-transitive imports, and then eventually reach a variable declaration only. So this rules out the dotted path because it requires traversal of a mod edge, which is not allowed by this regular expression. So by now, I hope you have a slight feeling about how scope graphs work and how you can model all sorts of different name binding patterns with them. But as I said, there's a huge overhead in actually computing those resolution paths. And in order to show where the overhead is, I need to quickly go through the algorithm that we use to compute those paths. I will not explain it fully. That will become clear later in the talk. But I want to point out that it's basically two steps. First of all, we check the scope that we are currently in, which is the S argument. If it is a valid declaration, and if so, we include it in the set E, which eventually is the environment that we return, which is a set of scopes that our variable can resolve to. And after that, we traverse all outgoing edges to find possibly more valid declarations. And I especially want to draw attention to these derivatives. So what are those? A derivative is basically, it's pronounced as computing a derivative of R with respect to label L. That yields a new derivative, R prime in this definition, and it's defined as follows. If there was a word LW in the original regular expression, it will ensure that the suffix of that word W will be in the new regular expression. So, for example, when you look at the first example, if you have a regular expression that matches the single word L1, L2, and compute the derivative with respect to label 1, it will return the regular expression that matches label 2, because that's the suffix of that word. And there are, you look at a second example, which matches optionally an L1 and then a non-zero sequence of L2, and you would actually traverse a single L2 label. The remaining regular expression will be the closure over L2. But thirdly, when you would instead compute a derivative with respect to label 3, there's no such word in the original regular expression, so you end up with the empty regular expression. And so let us look how that works for the example that we had. For the query that I showed, the initial S will be B because we started in scope B. We have this regular expression, and the N argument, which is the name of the declaration that we are looking for, is X. So when we have traversed the IMP label, we have computed the derivative over with respect to RMP of the original regular expression in the recursive call, which gives us the var label, the var regular expression once we arrived in scope A. And when we again traverse the second var label, we have the regular expression that matches the empty word. So in this case, these derivatives follow, ensure that we only follow valid paths. And it also shows that once we are in scope S, then in our if statement, the second condition will be true, because obviously the empty word is in the empty word in the epsilon regular expression. However, profiling shows that there's very much overhead in computing those derivatives. It's 12.5%, and that's not what we like. So we want to get rid of it. And luckily, that's possible because we know those regular expressions statically. They are part of the type system specification and not of the object program. So what we can do is we can derive specialized versions of this resolve algorithm for a particular regular expression. So I will first show it by using the empty regular expression because it's a pretty easy example. When we know it statically, I've marked the parts that we can pre-compute statically in gray. And we will use that to derive a specialized version of this resolution algorithm. So the first step is initializing our result variable, which we cannot pre-compute, so simply copy this statement. Secondly, we have this if statement, which we can compute a part statically already, because obviously, again, the empty word is in the empty irregular expression, so that evaluates to true, and we can eliminate that condition. So we copy the remaining of this if statement into our specialized version, because, we can only dynamically check whether our scope is really a valid scope. For the second part, this double for loop, we can be sure that there's actually no valid derivative of the no label which has a valid derivative for the empty irregular expression. I mean, when there's only the empty word in the language, you cannot have a word that has a particular label as a prefix. So we can completely eliminate these for loop. So that leaves us with a return statement that we also copied. And in this way, we found a resolve algorithm for a particular regular expression, which is way more efficient to execute. We can also do this for more complex regular expressions. So I'm going to talk through the original regular expression that we had. Again, we need to copy the initial environment initialization. But at this point, we can statically evaluate whether the empty word is in this regular expression. This is not the case because the regular expression at the end forces us to traverse over a var label. So as this condition evaluates to false by constant propagation, we can just skip this if statement. Now we can iterate over the label set again statically. So first we try to evaluate this condition for the label var. In that case, there exists a derivative, so the if condition holds, and we copy the inner for loop into our new algorithm. But please observe that instead of using the generic recursive call to resolve, we refer to our specialized version. So we pre-computed our derivative in the recursive call and found the correct specialized version to insert in our new algorithm. We can do the same for the lex label, which will look similar, but has a different references a different specialized version of resolve because the derivative is different. And again, the same for the import label. For the mod label, however, such a derivative does not exist. So we do not have to include the inner for loop specialized for the mod label. So we go over that, copy our return statement, and we have our specialized version for this more complicated regular expression. And please observe that in this right version of the algorithm, there are no derivatives anymore. We have statically pre-computed all those derivatives, so we removed this overhead from our type checker. So in summary, what have we done? We envisioned that we should write high-level specifications that we automatically generate type checkers for, but we added a second pass to this Statix backend which ensure that the type checkers that we generate are now a lot faster. Actually, in the paper, there's much more. We can also encode shadowing policies using scope graphs, using partial orders on labels. That's also incorporated in the resolution algorithm, which is explained there. And these label orders even give 35% overhead. But luckily, we can also statically pre-compute all those label orders and fold the algorithm over that and get rid of all that overhead again. We have incorporated these specialized algorithms in a nice intermediate representation, on which we applied additional optimizations such as common sub-expression elimination. We of course evaluated this approach. We used a specification for a large subset of Java, for which we then synthesized a Java type checker. We ran the type checker over 3 different Apache Commons projects, namely CSV, IO, and Lang3. For the CSV project, we micro-benchmarked the execution of each individual query. And for all of these 3 projects, we benchmarked the overall runtime of those type checkers. So what did that give us? For the micro-benchmarks, the histogram is shown on the left. Please observe that the x-axis is in log scale, so don't be put off by that. On average, the speed up of the algorithm on individual queries is 7.7 times. So queries got a lot faster. There's a tiny fraction of queries below the 0 that were slowed down a bit. But there's also a pretty heavy tail of queries that got 100x or more speedups. And what does that give for type checkers? That's shown in the table on the right. We have evaluated it on projects of different sizes with plain running times from 7 seconds to 88. And those got a speed up of 38 to 48%, so almost halving the runtime of those type checkers. Before I conclude, I want to zoom out a bit. So what made this approach work so well? I think it's because 2 things came together. First of all, we have a single language construct, these queries, that had a very complex interpretation, the resolve algorithm that I showed you. And secondly, part of the algorithm was part of the object languages, was in the AST, namely the regular expressions. And when those come together, specialization is a very powerful technique. But I think this is more common for declarative languages, as declarative languages intend to hide complexity from their users and incorporate it in their backends. It's natural to expect more complicated algorithms in interpreters of declarative languages. So therefore, I think this research suggests that specialization is very powerful, especially for declarative languages. So to conclude, what should you take away from this talk? First of all, using scope graphs, you can model all kinds of name-binding patterns in type checkers for which you can automatically generate. You can model all kinds of name-binding patterns for type systems, for which you can generate type checkers that have now become even more efficient. And specialization is especially powerful optimization technique for declarative languages. Thank you for your attention.
Okay, is there any question from the audience?
It's a great idea to use a scope graph to do some type checking, and you also mentioned you have some evaluations on the Java type checker, and we know that in Java programs, many in code they are importing library, classes, method, so which I think I'm just curious if this type checker if the scope graph is slow or lazily grown by loading the symbols that you parse from the class files, in particular, the class files of the standard library, because sometimes the code may refer to some Java standard library, and they have plenty of methods, symbols defined there. So is there any strategy that you can to limit the size of the scope graph while doing type checking? Because I think that also it has some impact on the efficiency.
Yes, so currently, we do not have lazy loading of scope graphs. We support exporting scope graphs of particular programs in library files that essentially form a summary of the library, which is more easy to load than type checking the whole library over again. It might be an interesting idea to explore in the future. So thank you for that suggestion.
Okay, I also have a question. In this particular application, wouldn't it be so much simpler and mostly as fast, maybe just a little bit slower, to use some simple memorization techniques so that every time you look up for a variable in a certain scope, you can keep a cache local to the scope so that you can do the complex computation only one time instead of having to do this kind of much more complicated code optimization?
Yes, so we have considered that, but there are a few subtleties in the algorithm that, I didn't show in the presentation, but are in the paper. For example, we prevent cyclic paths to ensure termination of the algorithm, and that ensures that, every resolution has a different prefix, so you cannot easily cache this bottom-up resolution strategy anymore. Although, it looks there are a few subtleties which make caching a bit more problematic. Basically, also because in the algorithm, that's a second reason. I can quickly show it. I simplified this thing to, just an equality comparison over scope should be equal to a name. But in essence, we allow arbitrary predicates over scope to be at that position. And, you would use a predicate as a key for your cache, which also doesn't work very well. So those are the complex things in this algorithm that make it uneasy to cache them.
Okay. It's sorry, I feel like we're a little bit out of time. So maybe we can go to our next and last speaker.